I'm going to go through some of these big questions in astronomy and astrophysics, and it might be useful to think, well, when would you come across such big questions? And you might think, well, some people will know them, but in fact, there are regular reviews that go on. And there are various sources of information that you might come across if you wanted to look at lists of big questions. And they usually come from national panel advisory reports. So, for example, the UK Particle Astrophysics report, which I'll show you a pretty picture of the front in a minute, or the STFC roadmap. Anything that's got the word roadmap on it usually means there are lots of interesting questions. Or the US 2011 Decadal Review. The thing to bear in mind about these is that they're usually investigated because they want to decide what they're going to fund. There's a limited amount of funds, so people with particular interests try and put forward the case as to why you should fund this particular very large radio telescope, or this Cherenkov array, or this X-ray observatory. And so the advisory panel reports tend to try and come up, first of all, with a list of questions that they consider to be important, and then they think which of the following instruments should we fund in order to get most money or most science for our buck. And so this would be the Particle Advisory Physics report, which will be out soon. There's the US Decadal Review, which goes on once every 10 years, as the name suggests. And this is a very big thing in the US for deciding quite what the direction of their science is going to be. And there's the Science and Technologies Facilities Council Challengers Roadmap. Looking at all of these, actually, I've found that the STFC one was somewhat better organised than the others. So, rather than giving you my own particular research areas are black holes in the context of active galactic nuclei and their relationship to the variability of X-ray binary systems and how the relationship between different wavebands in active galaxies goes on. So I could have given you 25 minutes of that and 3 minutes of the rest, but I've tried to split it up a bit more and give you an overview of what most people think the important questions are. So here we can see it starts off with how did the universe begin and how is it evolving? In other words, the cosmology questions. If you're an astronomer and you can't sell cosmology to anybody, then you're not doing a very good job. Everybody wants to know about cosmology. The next thing here, the next bunch is stars and planetary systems. How did they develop? And the life question. Life is always a very good thing to get into your proposals if you want to be funded. So the life question will come in. I would like to go and study distant active galaxies because I'm really very interested in the life forms that might be there. No, but maybe I'll get funding for it. Then, this bit here is mainly particle physics. See, what are the fundamental constituents and fabric of the universe and how do they interact? I'm going to go into these areas in a bit more detail shortly, but I'm giving you the overview. But this is mainly the particle physics bit, and Nick Evans will be talking to you, I think, in about 2 or 3 weeks to bring out the particle physics aspects. Then the other good, or very trendy thing at the moment is the extreme universe. So the extreme universe is really things like black holes, very high energy physics, TV astronomy, what happens around about black holes. I'm sure Nils will be saying a bit more about this. I'll say some observational things about it as we get on. One of the things also that you note from all of this is that there is a big relationship between particle physics, mathematics, particularly the general relativity, gravitation mathematics, and astronomy. And so one of the things that we've been trying to build up at Southampton, and it's just beginning to start, is something called STAG, which is Southampton Theory, Astronomy and Gravitation. And we're trying to pull together themes in these different directions because I think the future will hold a lot on the boundaries between particle physics and astronomy or particle physics and mathematics. And I'm pleased to see we're very slowly getting going largely I have to say because maths have put some money, we haven't, but maths have done, or credit to them. Okay, so I'm now going to move on and talk a little bit about how did the universe begin and how is it evolving. And these various questions here are the ones just taken straight from the SDFC roadmap site. So the questions here are, what's the physics of the early universe? What's the particle interactions? This is really something that I'm going to leave to Nick Evans, but these are the questions about how did inflation start? And so that's something that is of fundamental importance, but it's not something I'm really going to touch on enormously here as an astronomer. I'll say a little bit more about how did structure first form. We see in the universe round about us a very highly fragmented place. So in some places the density is very high in a galaxy. Outside the galaxy it's very, very low. So there's a great difference in density between the places that have mass and the places that don't. That wasn't the case in the early universe, as we'll look at in a minute. And so how did we go from the much smoother early universe to the structures that we see today? These are big questions. What are the roles of dark matter and dark energy? I'll talk a little bit more about those, not very much, because, again, they're the sort of things which astronomers have shown the need for dark matter and dark energy to explain the dynamics of the universe, but really we need particle physicists to give us a theory of what on earth this dark energy could be. More on that later. When were the first stars, black holes and galaxies born? It is thought that probably the first things that formed in the universe were very massive stars, maybe 100 or a few hundred solar masses. In the early universe, there weren't any heavy metals, and heavy metals essentially make the outer portions of stars opaque because they have lots of electrons and the radiation can push against these electrons and they blow the stars apart. So in the present day universe we don't have any of these because the present day universe is full of heavy metals and the stars have got enough of heavy metals to get blown apart if they were too big. But in the early universe the stars were basically just hydrogen, a bit of helium, and so they could be enormously big. And at the end of their lives, which were very short, they would then form supermassive black holes, they would form massive black holes, which are the seeds, we think, of the supermassive black holes that you find in the nucleus of every galaxy. None of this is certain, and these are the sort of questions that people would like to know. Is that really what happened in the very early universe? And if so, how did the universe evolve in such a way that the black holes seeds, which might have been maybe 50 solar masses, how did they get together with the other material that was there and actually find their way to the middle of proto-galaxies, and how did the whole thing then evolve? Indeed, how did the emission from those black holes affect the evolution of the surrounding material, the surrounding galaxies? So the links between black hole evolution and galaxy evolution are not known at all yet. So that's a bit about how galaxies might evolve. And there's a bit here that I'm not really going to say anything much about, A6, how are stars born and how do they evolve. It's another large and important topic, binary star evolution. For example, the supernovae, which we use, and which I'll show a little bit about later, as distance probes for the early universe, they mostly come around from the explosion of white dwarf stars. And these white dwarfs are almost certainly in binary systems, and what happens is material goes slowly from the other star onto the white dwarfs. Once it exceeds a critical mass, the Chandrasekhar limit, it goes bang, produces the supernova. Now, we assume that the supernova is going to be the same every time that happens, because it's going to pass this particular mass limit, and that's a bit like a thermostat. As soon as you exceed the limit, it goes bang. But we don't really know these processes very well, and it's important to us to understand stellar evolution, binary evolution, so that we can understand the whole of astronomy, indeed the evolution of supernovae, which are critical for our measurement of the geometry of the universe. So there's a whole load in how stars are born that I just don't really have time to say very much about here. When did reionization occur? This is another big question. In the very early universe, very, very early universe, it was highly ionized. And that meant that photons cannot reach us from the very early universe because they scatter from the very many free electrons that were available there. So you can't see that. There's a particular time when the universe became non-ionized, it became neutral. That's called the last scattering surface, and that's what we see on the microwave background. And then we can start to see photons coming towards us then. But later on, stars and galaxies and supermassive black holes formed, and they put out ultraviolet photons which ionized the universe again. So there's a mushy period where the universe is neutral, when galaxies and stars are forming, and then out of the other end it suddenly becomes neutral again, and that's important because if it wasn't neutral, then we wouldn't be able to see back to this early stage, which is known as the Dark Ages, because the hydrogen atoms would just absorb the photons that we were trying to look at. So the whole process of when the universe became reionized is important, and what provided the photons for that. Was it early stars? Maybe it was active galaxies. We don't really know. I've mentioned active galaxies. Active galaxies, these are the galaxies which have supermassive black holes in the middle, and they produce a lot of energy. Material pouring onto a supermassive black hole forms an accretion disk, and that emits a lot of radiation. It's a load of energy that these black holes give out, both as radiation and also as powerful jets. And they squirt that energy back into their surroundings. And it seems that this energy is very important for determining how many very big stars we might form and how many very little stars we might form. Because as soon as this jet starts going and belting material back into the galaxy surroundings, it can stop star formation. And so we have to reconcile our understanding of the number of galaxies that we have, the relative number of very big ones and very small ones, with the energetics that are required to make that happen. And so that's something I'll mention a little bit more later on. This, to remind you, is probably the most important picture we have for our understanding of the early universe. This is from the Wilkinson Microwave Anisotropy Probe, and it's observations of the microwave background. And we're looking here at fluctuations, and the fluctuations are really tiny. The whole thing here has an overall spectrum which is very similar to a black body at about 2.7 Kelvin. But there are little fluctuations here and there at the level of about 10 to the minus 5, very small. But they do exist, and these are the fluctuations which eventually grow and give us the galaxies that we can see now. And so how those fluctuations grow is very important. As I mentioned earlier, this thing that we're looking at here is essentially the wall at the end of the universe. It's the wall beyond which we can't see with photons because it's highly ionized. This is the place where it becomes neutral again, and you can actually work out in redshift terms how far away that has to be, because it's at a temperature here of a few thousand degrees. Take a photon with a wavelength of a few thousand degrees, stretch it by a factor of about 2,000 to get to the present universe, and it becomes a photon of about 2.7 Kelvin, and that gives you the redshift, or the distance, to this last scattering surface. So, now one of the big things, it's astounding what theoretical cosmologists have obtained from study of these fluctuations. You can see, if you look, that there are lots of fluctuations. If I can find my probe again, it's disappeared. Here we go. There are lots of fluctuations on about a 1 degree scale size. There are fluctuations on larger scale size. And in order to quantify these different fluctuations, we create something called a power spectrum. And it gives us an idea of how much variability power there is on different scales. And that looks like this. And so here we can see at scales of about 1 degree, lots of power, but there's also power on, here we've got shorter scales, less than a degree, and up here, long time scales, 90 degrees. And we can see that the data here is described by these dots. And the red line is a theoretical model based on what we think the universe is made of. And this contains information about how much baryonic matter there is, how much non-baryonic but real matter, and how much of this other stuff that we'll talk about later, the dark energy there is. And this tells us, from fitting these theoretical models, that we live in a universe that's basically flat. In other words, the angles inside a triangle will add up to 180 degrees. It's basically flat Euclidean geometry. And it tells us about the mass enclosed in the universe. It tells us an enormous amount. And so this has been very important for our understanding. What do we do next? Well, you can see down here, at the shorter timescale, it begins to get ratty. And there's an experiment called Planck, which is going to do something, well, it's up at the moment in doing it, and it's going to define the shape of the microwave background on shorter scale sizes here. Come back to me. And improve our understanding of the knowledge of the geometry of the universe. There's another thing that can happen, and this is just really in the offing. The microwave background is slightly polarized. It's really hard to measure that polarization. And the polarization, which is meant to be these little lines here, superimposed, the polarization tells us about what went on behind the wall. In other words, in the very, very, very early universe. And that can have come from things like inflation. It can come from things that particle physicists will tell you about symmetry breaking activities in the very early universe. It tells us about what's happening beyond what we can see with electromagnetic radiation. And so one of the things that we could perhaps find out if we could measure the polarization properly would be about the gravity waves in the early universe, and maybe a little bit more about inflation if we could measure this polarization accurately. So this is a big game in the future, and it's probably the next thing in the microwave background studies. So, the evolution of structure. Do current models explain the observations? And we do have some idea of the way we just take a lot of particles and we let gravity pull them together. But we have to add in bits of extra physics, so that we have to add in a bit of energy from the AGN maybe. And these are the sort of things that we get at the moment. And these are models carried out by people like the Durham Cosmology Simulation Group. And you can see how from a very smooth early universe, you get the structure that we can see today. And it's reasonably correct. It's not perfect. It doesn't explain perfectly the relative distribution of the number of bright galaxies compared to the number of faint galaxies. And so we might want to improve that by putting in more knowledge of physics about how we can put energy back in from supernovae, from active galaxies. Here's another one of the same sort of thing. This is just another simulation. There's an awful lot of work goes on in theoretical astronomy in making these wonderful simulations of how the universe evolves. And a big job is to make sure that your simulations contain the right physics to explain what we see. And if they don't explain what we see, then we have to think of new bits of physics. Right, it'll stop again in a bit. Right. Okay. So this is galaxies forming. Quite pretty. Let's look now at the life questions. How do stars and planetary systems develop, and is life unique to our particular planet? So, Is our own planetary system typical? What does the sun do to us? How does the sun affect us? Is there life anywhere else in the universe? So, there's been a lot of effort over the last decade or two to try and find planetary systems apart from our own. And that's been very successful, and there are a few hundred now known, mainly found either from looking at the movement of stars as planets go round them, they'll wobble, or maybe observing as planets go in front of stars and you can see the light go down. There are a number of ways, and this is one example of the sort of results that are known. So this is a particularly well-studied system, this particular star, and round about here you can see there are a number of potential planets that have been found. The star has been blanked out in the middle. So the next thing that really we need to do is, I think there are missions coming up, they'll be launched by ESA in the next few months, called Gaia, which will find many, many more planetary systems. But ideally, we'd like to see if any of them are capable of detecting life, of holding life. So have they got any water on them? And there was a mission that was proposed, but unfortunately not funded just yet, called Darwin. And there you would try and take spectra of these planets. And if you could take the spectra, particularly in the infrared band, you might be able to see signs of water vapour. So I think the next step really in the life search is to try and detect planets. First of all, they have to be in the Goldilocks zone, as it's referred to. So they have to be in just the right place. Not too hot, not too cold. If they're too close to their sun, then water boils. If they're too far away, water freezes. So you can work out how far away from the star it has to be to have a chance of having liquid water, and we're going to equate liquid water with life. It may be there are silicon-based life forms that are quite happy living inside Mercury, on the surface of Mercury, but for the time being, we're not going with that, and we're going to go with the water-based ones. So we'll see if we can find water in any way round about these stars. How about the sun? Well, there's a lot of study going on at the sun. There's a number of missions doing it, SOHO, and the things that concern us quite often from the sun is, see this big thing here on the side? There are big coronal mass ejections. These things are huge ejections of material which come out as part of the solar wind, and about 2 days later they hit the Earth and cause trouble to power lines if they're hit. So can we understand the sun? Can we maybe predict these? And so there's quite a lot of work going on, which I'm not going to say much more now, about trying to understand the sun itself. It's our closest star, and there are a lot of things that we can learn from it. For example, a lot of the temperature of the corona of the sun is about 1 million degrees. So how can that be? Because it's very hot in the middle, but not on the outside generally. How can the corona be so hot? And so there's something that's heating it up, and it's probably magnetic field line reconnection. So when magnetic field lines, one going that way, one going the other, reconnect, they can give up all their energy to whatever happens to be around, and they can accelerate particles. And we think that the same process that accelerates particles in the sun also applies in active galaxies, in accreting black holes. And so there are synergies between these different branches of physics. The life-water question on Mars. Very major, gets a lot of funding, and here are some pictures of Mars, which are, apparently these things show up on sunnier south-facing bits of Mars, and they come and go with the Martian seasons, and it's thought that they're the result of melting of salty, brackish water, perhaps round about here, running down and giving rise to these channels. So, although there's no proof, there are suspicious indications like this that there might be some flowing water still on Mars. These are the sort of things that planetary astronomers are searching very hard to find, with things like the ESA Mars Express observer, which has been observing, taking pictures, and also you will have heard recently about the NASA Mars Curiosity rover, which is now up on Mars, and so this is a picture taken of some nearby rocks. This is the rover, it's moving around on the surface of Mars, and they're trying to crunch up some of the rocks to see if there's evidence for any ancient life. Are there any bacteria in these rocks which might say that life has ever existed there? So, the next bits, these are the particle physics bits mainly. What are the fundamental constituents and fabric of the universe, and how do they interact? So, what are the fundamental particles? What's the nature of space-time? Is there any unified framework to reconcile the different forces of, that we know of in the universe? One should say the big one here would be quantum gravity. So if someone can unify the gravity with the other three fundamental forces of nature, electromagnetic and nuclear strong and nuclear weak, then there's a decent chance of a Nobel Prize there, I would think. Einstein spent most of his life after General Relativity trying to track it. But if you have an IQ of about 300, then you know this is the field for you, I feel. It's a really major question, but very difficult. Other questions: what's the nature of dark matter? Well, astronomers have shown from dynamics. I think I've got one or two pictures. No. Well, no. From the motion of galaxies, astronomers have shown that there has to be more matter than you can see in the stars. So you can just look at the speeds with which stars go round galaxies, and they go round much faster than they ought to if the only matter that was there was the matter that's in stars. You need more mass to hold the stars in their orbits. And the same thing we found in big clusters of galaxies. The galaxies are moving around faster than they ought to be if the only mass you could see was stars. So we know there's dark matter, we just don't know what it is. And so people sit down deep minds, try and keep out anything else that might hit, in the hope that a dark matter particle, which, because it's dark, it doesn't interact with other material very well, might get through a few kilometres of the Earth and then maybe interact with our big detector deep under the ground. So there are big searches going on to try and find dark matter, and there are theoretical studies going on to try and come up with dark matter particles, like the lightest supersymmetry particle may be a good candidate. We don't yet know what it is. Dark energy, I'll say a brief bit about that more, is even worse, and more about that in a second. What's the nature of nuclear hadronic matter? What's the origin of the matter-antimatter asymmetry? These are questions which I'm sure Nick Evans will be answering for you in a couple of weeks' time. But I shall move on to say a little bit about dark energy. So, for those of you who haven't been following the dark energy thing, the observations that have really clinched dark energy are that distant supernovae, these standard candles that we think of, are moving away a bit more slowly than we might expect. So up here on the left-hand side, you can see these are from the observations that got the Nobel Prize last year. This is the velocity, and this is the distance. And you work out the distance by saying, how faint is this supernova? I can see a supernova. I know what its absolute luminosity is because I'm prepared to guess that I understand stellar evolution maybe well enough. We'd like to know better. So I know its luminosity. I can see how bright it is, so I can work out its luminosity distance. And that's here. I can then measure its recession velocity, and I get this plot. And what I find is that this plot curves as we go to large distances. So in other words, at the nearby universe down here, things have speeded up. The universe has accelerated because if we extrapolated the nearby universe back to the far universe, here we are, if we extrapolate what's happening in the nearby universe back to the far universe, we'd be up here, we'd expect a greater velocity than we can see. So the nearby universe is accelerating, the universe's expansion is accelerating. Why on earth is that? And so what you need to do that is something that pushes. And the dark energy, which was, as you probably have come across, it was also known as the cosmological constant, because when Einstein first deduced his equations of general relativity, he came up with a constant. And he left it there, and later on he said, no, it's my greatest mistake, I should have just put it equal to 0. But in fact, this constant explains very well this expansion of the universe. And it's funny stuff, this dark energy. What it has to do is it has to have a relationship between pressure and density with a W there, but W's -1. So that's not the same as in ordinary matter. Ordinary matter W has to be +1. But here, it has to be -1. So what on earth this stuff is just completely unknown, and it's definitely a quantum field theory question and not an astronomical observation. Astronomers can show it's there, but not tell you at the moment what it is. Future questions, you might say, is it exactly 1? Or is W maybe, does it vary with time? And so the supernova people are now carrying on with their studies to try and find out, can they constrain W any better than just knowing. At the moment it looks like it's close to 1, but it could be deviate by 1 enough to be interesting. So finally, the extreme universe. And here we're talking about things close to black holes. Quantum gravity might tell you what's happening inside black holes, who knows? But how do the laws of physics work when driven to extremes? And maybe what can high energy particles, gravitational waves tell us about the extreme universe? Leave the gravitational waves to Nils in the next talk. And how do the ultra-compact objects form? And how does extreme gravity impact on their surroundings? And just another plug for our STAG initiative. So this is an example of what we might think of as extreme gravity. Down here, this is a binary system, and in the middle there is a compact object which is the result of stellar evolution. And if it was a small object that collapsed, that could be, in the middle there, it might be a white dwarf. If it was a massive object that collapsed, it might be a black hole. And we get radiation out from this accretion disk as material spirals in towards the compact object. So that's what you see on a stellar scale, but you get the same things on a galactic scale. And let me just do this simulation here. We're zooming in now towards the middle of this galaxy, and what we'll see when we get there is, again, we'll see an accretion disk, similar to what we saw in the stellar system, but the accretion disk, we're now going in deep down towards the middle. We often see jets coming out like this. Here's a cut through of the accretion disk. We can see it may be highly expanded at the inside edge, perhaps due to being inflated by massive amounts of energy coming out from the black hole. So questions we might want to answer here are, what is the structure of that accretion disk? How does it depend on the accretion rate flowing in? How are the jets formed? How are the jets related to the disk? We think they are strongly related, and it might be that magnetic fields come up from the disk and get swirled round and get swirled into some sort of a channel, which then funnels material out. So there's an awful lot of stuff to be found out about the disk-jet connection, the structure of accretion disks, and the structure of jets. These very compact systems emit copious quantities of high-energy radiation, X-rays, gamma rays. They also emit radio emission and sometimes also optical emission. So here's just a couple of the bands. We haven't got time to go through all of them. And you can see that there's very rapidly variable emission on a number of different timescales. Here's the X-ray emission at the top from this particular object. Here's the gamma ray emission. They don't look very much like each other. And so what we want to understand is, where do these bits of emission come from? Do they come from the jet? Do they come from down near the black hole? How does this accretion process work? How do we actually turn gravitational potential energy into accelerating particles and radiation? So how are the radiated particles accelerate? How does that work? And now we can go to gamma rays here. This is in the giga electron volts. We're just starting to be able to make observations at TeV, 10 to 12 electron volts, which is energy about the same as a tennis ball, an enormous amount in each photon. And how on earth do you accelerate particles up to sufficient energies that they can produce photons that powerful? And tests of black holes, observational tests here, can we use the X-ray emissions from black holes as observational tests of general relativity? So this is a very famous picture from Tanaka. And what we're looking at here is an X-ray spectrum. So we're going from low X-ray energies up to high energy X-rays. And the top picture gives you the whole spectrum. So there's a big continuum, but there are little blips here. There are excesses. So if we take away the smooth continuum, these are the residuals at the bottom. And the residuals, you can see, there's a big lump here. Now, we think that lump is from fluorescent ion emission. In other words, if you get an ion atom and you eject the innermost electron from that ion atom, then the next electron will drop down and it will give you a photon with an energy of 6.4 kiloelectron volts, which is about there. But it's not a narrow line, it's a very broad line. And we think the broadening is caused by a number of effects. We think that the fluorescent line is produced by the inner edge of the accretion disk. We think that X-rays, maybe from some surrounding corona, come down and illuminate the inner edge of the disk, and then they produce this fluorescent emission. But the disk is spinning round, so it's spinning at enormous velocities, close to the speed of light, if it's right in close at the black hole. And so a relativistic Doppler effect is going to have a big effect on what you see. And the stuff going away from us will be shifted to lower energies. Also, the photons have to get out from this deep gravitational potential well. So we get a gravitational together or Nils area. And so, can we make sensitive observations with X-ray instruments that provide good enough spectra that enable us to test what's actually happening down near black holes? So, I will conclude briefly with saying there are an awful lot of interesting questions in astronomy. And if you're considering a career in astronomy, there are a number of things I would say to you. Choose your science area. Lots of areas are interesting. Choose your science area, but you also need to decide whether you prefer to do something which is more observational or more theoretical. Actually, somewhere in the middle is good if you can manage both, because theorists who only want you to give them some observations and don't care where they've come from will often provide a theory that explains incorrect data. Similarly, observers who don't really have a good grasp of the underlying theory of why they're making the observations won't be all that useful either. If you do carry out, it's not an easy career route, I would have to say. And so the route through to permanent academic jobs is tricky. But I always say this, I say, consider it carefully, you're very sure you want to do this, you really shouldn't do it. And then I see all these people years afterwards and say, oh, we entirely ignore your advice and we're now happily doing it. So, but do take the caveat that it's tricky. Also, if you wish to be very rich, this is not the ideal route. If you want to be very rich, you should be in the law department, I think. But you will be quite comfortable. Your salaries will be quite comfortable, but you will not be very rich. The other final thing I would say, for PhDs, don't just restrict yourself to the UK. Consider other countries. The US, for example, they speak a language that's nearly the same as ours. And you might be able to make yourself understood there. And it's not a bad thing to do. Go and do a PhD in one of the better-known universities in the States and then come back. Very worthwhile. You'll also find you'll then build up the number of people you've got to give you references later on, which is always an important thing. If your languages aren't too bad, consider Germany. The Max Planck Institutes are very good. They mainly operate in English, though it's handy if you can speak German. French is trickier. They tend to speak in French all the time, mostly. But there are countries in certain bits of Europe. Astronomy is a very multinational business these days, so do consider places outside the UK as well. And I'll stop at this point.